Hello everyone, my name is Ricardo, and this is the Professor Ricardo Explains channel. In this video we explain the minimum surface of revolution based on the book Classical Mechanics by Goldstein. First, let me tell you that we have a playlist for the solutions of the Goldstein's classical mechanics problems, and another one for the solutions of the Sakurai's quantum mechanics problems. Help our channel subscribing and becoming a member. You will get access to exclusive members-only videos. Your like is also very helpful for our channel to continue helping students all over the world. Thank you for your support, and send your comments asking for the solutions of a problem you need. Minimum surface of revolution. This topic is inside the context of Calculus of Variations, Chapter 2 of Classical Mechanics by Goldstein. Consider the x, y, and z axes, and we will form a surface of revolution by taking some curve passing between two fixed endpoints, x1, y1, x2, y2, defining the xy plane. These 2 points defines the xy plane. And we will form the surface revolving this curve about the y-axis. Since we want the minimum surface of revolution, we need to find the curve for which the surface is a minimum. The area of a strip of that surface is 2 pi x ds. To make it easy, let's see the view from above. We see that the circumference with radius x is 2 pi x, and the area is 2 pi x times ds, the height of this strip. And what is ds? Well, it is the element, the infinitesimal element of length in a plane, which is the square root of dx squared plus dy squared. If we write dx squared as a factor inside the square root, that factor will multiply 1 plus dy dx squared. We can write that factor outside the square root, and using the notation we have already discussed that y dot is dy dx, and we obtain the area of a strip of the surface. Here in terms of ds, here in terms of dx. Now the total area is the integral over ds. Or, since we know ds is a function of dx, we integrate this equation over dx and obtain 2 pi, the integral of x, the square root of 1 plus y dot squared dx. We want to obtain the minimum surface of revolution. So the extremum of this surface is given by this well-known Euler equation. We are using the calculus of variation to calculate the minimum surface of revolution, where the function f in our case is given by x times the square root of 1 plus y dot squared. So now we need to find these partial derivatives. First, del f del y. It is equal to 0. There is no y on this function. What about del f del y dot? It is x times 1 over 2 times 1 plus y dot squared raised to the negative of 1 over 2 times 2 times y dot. This factor 2 will cancel out, and we will get x times y dot over the square root of 1 plus y dot squared. Well, let's use these two results into the Euler equation, and we will obtain d dx of this term equals 0. Since the derivative of this term is equal to 0, then this term equals a constant. Well, let's square this equation and obtain x squared y dot squared equals a squared times 1 plus y dot squared. The right-hand side will be a squared plus a squared y dot squared. And then let's write y dot squared as a factor, which will multiply x squared minus a squared. equals a squared. And then dy dx, which is y dot, is a over the square root of x squared minus a squared. If we integrate that, we will get that y is equal to a times the integral of dx over the square root of x squared minus a squared. And the result of that integral is the arc hyperbolic cosine of x over a. And b is the second constant of integration. Or we can rewrite this as x equals a hyperbolic cosine of y minus b over a. If you write b on the left-hand side, we will get y minus b over a, and then the hyperbolic cosine of that will be x over a. And then you can write a multiplying that hyperbolic cosine. And this is the equation of a catenary. So the solution to the minimal surface of revolution problem is a curve known as a catenary. We just solved the problem. But if you want to practice, there is this problem on chapter 2 by Goldstein, where we need to examine the symmetric case where x1 equals x2 and y2 equals the negative of y1. You can find this problem in our playlist, which contains many solutions of the Goldstein's classical mechanics problems. And here is problem 7 of chapter 2. Here is the conclusion of that problem, including a plot for the different scenarios. By the way, here we show that there is a mistake on the Goldstein's problem, as you can verify in our playlist. If this video was helpful, please help our channel subscribing and becoming a member. Your like is also very helpful. You can also share our videos to other students. Thank you.